Okay, so I'm going to pick it up from here to see how we're going to solve this guy based on some of those concepts. Well, what I'd recommend in terms of the last layer, when you're doing a 4x4, I'm going to go by the concept that basically these are all corners. Now my goal with the solve of this puzzle is no new algorithms. You shouldn't have to do that. But the fact that this is not only a supercube, that means the orientation has more specificity than this puzzle. You're also laden with a lot of concepts such as the parity problems that happen with this puzzle, but also false equivocations, and that can get kind of confusing, potentially necessitating long and drawn-out algorithms. We're going to prevent all of that, actually. So my recommendation is this. When you have a 4x4, I wouldn't go ahead and do it as I would have done the 3x3, which is orienting the edges or whatnot. I would say get the corners in first. Because that's what we're going to do with this. Get the corners in first at this point just to kind of see where things are at. So the first thing that I would do is maybe rotate the corners correctly. Well, that is easy to do. Just do RID, RD until you have all these rotated correctly, just to eliminate confusion. So I'm going to pattern this solve based on this solve, but I'm going to start off with this so there's less confusion. So let's rotate these corners up by doing RID, RD, and again, until this is up. It is. And I'm going to move this over here. RID. I've got the corners rotated up. The next thing that I want to do is I want to put the corners in the proper position. So I see these two corners are in. These are over here. I've got to do a corner swap to put these in. Now notice I'm not even thinking about the edges right now. I'm just thinking about the corners. That's going to be key in terms of what I think is the simplest solve of this guy. So what that's going to entail is a corner swap. I'm going to go ahead and swap these two. Now understand that when I say corner swap, I'm not really doing a single swap. That breaks the parity of any kind of a puzzle. What I'm really doing is this stays the same. This goes to here, this goes to here, and this goes to here, which means that these guys never lose their orientation. However, this does orient itself appropriately with this guy. The edges are going to be out, but that's okay. We're not worrying about the edges yet. So let's go ahead and do that algorithm. 2R U, 2R UI, 2R UI D, 2R UI, 2R U, 2R. This goes back, and as you can see, all the corners are in. Let's stop with that for a second, and let's move to here and do exactly the same thing. So without worrying about the centers and the edges or anything like that, let's go ahead and put the corners in. So looking at it, I have to make sure that things are oriented, and it might take a little bit of doing, but if I move this, say, in this position, this is correct, this is not, and this is not. What I can do is try to find the two that are in, and I don't have any two that are in, actually. So what I can do is I can do some corner permuting algorithms to get things where they're supposed to be. So this is in. Is this in? Well, this is red. This is red, green, and blue. You can see this is red, green, and blue. So this is actually correct. It's just not oriented correctly. Now it was easy to see which ones were rotated correctly because the blue is on top. This one may be a little more difficult to see. But suffice to say, I know this is rotated wrong even though this is in, which means this belongs here and this belongs here. So I've got a situation here where this corner is in, this corner is in, this is not, and this is not. So that would entail a potential single swap. So does that represent something of a parity as a 3x3 to have to do just one single corner? And the answer is it does, but it might kind of surprise you as to why. So this corner is in, this one is in, these two have to be swapped. So it sounds like, well, this is a parity situation. But I know that in a 3x3 I can get something similar, right? This corner is in, and these two aren't. So they need to be swapped. So in looking at this, I can say, well, it must not be a parity situation because you can get that on a 3x3. But here's the rub. In the beginner's method, you never got this configuration. Even though I can put it in this configuration, you never got this configuration as you were solving. And the reason is because when you put the edges in, the corners automatically got themselves fixed. You can't have an issue with a single swap of a corner without having swapping of edges as well. So once you put the edges in, the corners magically got fixed. So though it would appear that, well, no, it's not a parity situation, you can get that with a 3x3. You actually won't get this in a 3x3 if you put the edges in, but you can get this on a 4x4 even if you put the edges in. So if we were to swap this, 2R U, 2R UI, 2R UID, 2R UI, 2R U, 2R, bring it back. So you can see now all the edges are in. You fix this and you fix the other as well. So if there's any questions on that, let me know. I can try to elucidate that further, but it is a parity situation. Even though I can recreate it here, it never would have been a problem once I put the edges in. In a 4x4, putting the edges in is no guarantee that you're not going to get this situation. So we're going to address this, and we're going to address this by stating, I know this is correct, this is correct. I don't want to rotate this quite yet because it's going to be difficult to know what this is supposed to be. I just have to swap these two, and that's what I'm going to do. Just like I did here, let's go ahead and swap these two. So that's 2R U, 2R UI, 2R UI D, 2R UI, 2R U, 2R, and this goes back. Now remember, I promised you no new algorithms. So what we have here is this is correct, this is the correct color configuration, this is correct, as is this. Now that I have these in the correct place, I can now do RIDA RDs until this is rotated right and this is rotated right. So let's go ahead and do that. RIDI RD, RIDI RD, not in yet. This has to match with red and yellow. RIDI RD, RIDI RD. Okay, we're very happy with this in this configuration. So we're going to tool this around, and I'll put this guy in. RIDI RD, RIDI RD. Is it right? Well, this is all fixed over here, so I turn this around and I see that this is correct and this is correct. So now all these edges, these corners rather, all these corners are in. So I have that in this configuration. Once I have that, now what I'm going to do is I'm going to move towards the edges. I'm going to have my sight on the edges. And I had to use the concepts of the 3x3 in order to really help guide me. Now this might cause some confusion with some people, but so how is this going to work? Well, first thing we have to do if we're going to get the cross is we have to decide how, so we have to rotate the edges correctly. So how do I know that the edges are rotated correctly? Well, here it's easy to tell because it's on the surface. It's on the surface here. I can tell that these aren't rotated correctly, so with a line I do F RU, RI, UI, FI, and I've got my cross. So no problems. So to here, if I were to look at the 3x3, the way that I know that it's correct is these have to be facing opposite each other. The same colors are facing opposite. So these are facing opposite, and these are facing opposite. If that happens, I know that this is correct. I know that they're rotated correctly. And as you can see, this is in, so all I have to do is permute these around to get them out. But it might not have looked like that. It might have looked like this. Okay, so here's one configuration that you might get. They're facing opposite ways, right? These are facing opposites. This is facing here, this is facing here, this is facing this way, this is facing this way. But as you can see, this is not correct. It's not correct because it's, well, it's not in right. What that means is that although they're facing opposite ways, these are rotated wrong. They're rotated wrong. So they have to be flipped. Both of these have to be flipped. So if you see this configuration, these two have to be flipped, and we treat this as though that were the L formation. So if you have an L, you hold it over here and do F, U, R, UI, RI, FI, and that'll flip it back. So now they're still facing opposite way, but now it's put in correctly. And when that happens, all I have to do is permute these around and do RU, RIU, R2U, RI, and then I keep doing this. To U, RI, and as you can see, all of these are in. Okay. If you saw that two were facing the same direction, the other configuration that you can have is F, R, U, R, I, U, I, F, I. So notice this, you see the reds are now facing the same way, and the blues are facing the same way. In the 3x3 version, there's only a couple configurations. Either they're all facing the same way, in which case two are rotated wrong, or they're all facing opposite ways, but two are rotated wrong, or they're all rotated correct. So when I see this, I'm thinking, okay, which one is rotated correctly? Well, it's pretty easy to surmise that this is rotated correctly, this is rotated correctly, this has to flip, and this has to flip, because these are facing the same way. If these are facing opposite ways, and these are facing opposite ways, then one of these two pairs has to flip. In this case, you can see this is in and this is in. This is facing the same as this is facing the same as this, so this is a line configuration, so we do F, R, U, R, I, U, I, F, I. Okay, taking a look at this, opposite and opposite. But here's the problem, this is in and this is in, but this isn't. So these are facing the opposite way, these are facing the opposite way, but this is in, and this is in, and these two aren't. So let's say try to put all the reds in. R, U, R, I, U, R, to U, R, I, and then do it again. R, U, R, I, U, R, to U, R, I. You can see that other configuration where these are in and these are out, even though they're facing opposite ways, which means these both have to flip. So hold it here and do F, U, R, U, I, R, I, F, I. Now notice when I had the L formation, I did F, R, U, R, I, U, I, F, I. No, when I had an L configuration, I did F, R, U, R, I, U, I, F, I. When I had a line, I did F, U, R, R, I, U, I, F, I. Again, it's just beginner's method. So then I can get this in. And again. Okay. So there you have it. So first off, taking a look at this, I can see that the two blues are pointing opposite ways, so I know that these are okay in conjunction with each other. However, the red are all pointing the same way in terms of rotation. This is pointing kind of in a clockwise manner, and this is also pointing in a clockwise manner. They're all sort of pointing in the same direction as they're spinning. These will bump into each other if they were to spin. So I know that these are okay, these are not opposite, but this is kind of an impossibility when it comes to a 3x3 solve. And the reason is because, as we showed in here, you can have both of these facing opposite. You can have all of them facing the same way, but you can't have one set opposite and the other set not opposite. That's exactly the same configuration as this, where this is wrong or this is wrong. These two are right. So you only have one that's wrong. So just kind of think about that. If you can understand that concept, the solve does become easier. But suffice to say, this configuration you would not get on a 3x3, which means it's a parity. This is unsolvable as a 3x3, so that's what I mean by a parity problem. A parity problem means that I've committed to reducing this puzzle to a 3x3, and I only want to do 3x3 moves. Those are the rules that I've applied to it. But I've actually scrambled this, I've actually reduced this in an impossible way, giving me a parity problem, rendering this impossible to solve as a 3x3. So I can no longer look at this as the odd layered puzzle that I reduced it to. I have to look at it once again as an even layered puzzle. And that has to do with the hidden pieces underneath. When I reduced it upside down, and I would have no way of knowing. So this is what I mean by a parity problem. It had everything to do with how I reduced it. So to get this back is I have to slice into my reduction by doing the Red Bull algorithm. Now what I call the Red Bull is a simple algorithm that flips this over. 2R, 2B, 2U, L. 2 up, RI, 2 up, R, 2 up, 2F, R, 2F, Li, 2B, 2R. And that flips it up, so that's okay. Now I call it Red Bull because 2R, 2B, 2U, 2L, R, BUL, Red Bull. It was just an easy way for me to remember what appeared to me to be a very cumbersome long algorithm, but it was easier for me to remember that way. So I'm going to do the same thing here, recognizing these are facing opposite ways, these are facing the same way. You can't have that. Either they're all facing the same way, these two are facing the same way, and these two are facing the same way, or they're all facing opposite ways, but you can't have one facing opposite way and the other set facing the same way. So I got to Red Bull something. Well, what's it going to be? Will it be this one? Will it be this one? At this point, it doesn't really matter. It's got to be one of them. This one, whoops, this one has a nice home over here. So let's Red Bull this guy. So 2R, 2B, 2U, L, 2 up, RI, 2 up, R, 2 up, 2F, R, 2F, LI, 2B, and 2R. Okay, so we like this configuration now. These are facing opposite ways, these are facing opposite ways, so we have it in this configuration over here. And that was a true parity, a parity of reduction. So the next step, once again, you've got the corners in, you oriented the corners correctly, you dealt with any parities that's happening with the edges. Now what you want to do is you want to go ahead and, without looking at the center, the next thing that I do is keeping the corners exactly where they are, because that's the ultimate calibration of an even layer puzzle, is let's go ahead and do edge swapping to get the edges in. So these edges are going to come in by adjacent edge swaps or opposite edge swaps. Remember, with a 3x3, the edges ruled the day. We put that in first, then we put the corners in last. Best to do it opposite with a 4x4, especially with one like this, which I'll show you why in a bit. So looking around, I can see that this orange needs to come into here. Now understand, every time I do an edge swap, I'm going to cause misplacement across these two edges here. So let's do an opposite edge swap here to get this orange where it needs to be over here. I'll hold it in this angle. 2R, 2U, 2R, 2U, 2R, 2U. So we're good here. We have misplacement here. And now I've got, well, I'll move this into here. This white can come to here. This orange can come here. So that's 2R, U, 2R, U, 2R, 2U, 2R, 2U, 2R, U, 2R, UI, 2R. Fix this, and now we have ourselves a little bit of a problem. We have ourselves a situation where if I only used 3x3 moves, I have to do a single swap. That's another impossibility. That's another parity. Now you can all see that this is an even layer puzzle, which means that I can swap these two and these two, so there's no impossibility here if these two were to swap and these two were to swap. But if I applied this to the rules of a 3x3, then this is a parity problem. I can't solve this as a 3x3. We have a problem here. So how would we get out of something like this? Well, so let's see if we can apply it to here. Apply it to here. I kind of reconfigure this a little bit. But suffice it to say, we've got the corners in. We've oriented them right. We've permuted them right. Now what I want to do is I want to get the edges in. We're pretty sure that we've got the edges in the right configuration, in that these are facing opposite ways and these are facing opposite ways. So what goes where? Well, this is flush over here, so it looks to me that this red belongs over here. So let's go ahead and flip these two. So I'm going to hold it here and I'm going to do an adjacent edge swap. Remember, keep your perspective about you. If you can keep your perspective, you don't have to think about weird and bizarre algorithms. Or perhaps you will. Anyway, so it's 2R, U, 2R, U, 2R, 2U, 2R, 2U, 2R, U, 2R, UI, 2R. Okay, now bear in mind, what I like about these algorithms is that it does not change the conformation of my edges. My corners rather. So these will stay the same. So let's take a look. We like this red one here, so that's fine. Now it did create placement issues here the same way that it did over here, so don't let that confuse you. Just keep holding it here. But notice something else. It flipped these edges. It also rotated the center. That was another thing that happened when you did your edge swaps that you didn't notice on these puzzles, because this rotated, but you wouldn't know because there's equivalency of rotation. This one does not. So with this in, what else needs to go in? Well, it appears that this is the wrong blue. So let's do an opposite edge swap to get this blue to where it needs to be over here, and this will come over here. And this will get this misplacement out as well. 2R, 2U, 2R, 2U, 2R, 2U. All right, so that's okay. Ignore the center. We're going to hit that last. We've got this in and we've got this in, just like we wanted, and now we've got these two. So these two need to be swapped. But this is the same configuration as this, a single swap, and that's not going to work if I try it as a 3x3. So there's no doubt about it, this is a parity of reduction, and the only way that we're going to make this work is we have to dive into our reduced edges to make this work. In a 4x4, here's how I would do it. What I would do is get them away from being adjacent to each other and get the two that need to be flipped opposite each other. So I'm going to go ahead and put this in, which is going to create misplacement by doing an adjacent edge swap, then an opposite edge swap to get this misplacement back, and then put these back away from each other. So if you have it adjacent, go ahead and swap them. 2RU, 2RU, 2R, 2U, 2R, 2U, 2RU, 2R, UI, 2R. Okay? We've got misplacement over here. But we're not going to deal with it at this level. Trust me, it's going to be useful to not. Let's go ahead and do an opposite edge swap so that we can get these back in. 2R, 2U, 2R, 2U, 2R, 2U. So that's the first step. What I want to have is a configuration where the opposites have to be dealt with. So too, when I see this, let's go ahead and do that. Let's go ahead and get this in. It's going to create misplacement over here across. Once you get these guys in, it's going to cause misplacement across these edges and rotate the center. Once I do an adjacent edge swap, I'm now going to do an opposite edge swap after that in order to get the configuration that I wanted here. So do your adjacent edge swap. 2R, U, 2R, U, 2R, 2U, 2R, 2U, 2R, U, 2R, UI, 2R. Okay, fine. Looking good. These are all in. This rotated. Don't worry about that yet. Misplacement over here. So now we're going to do an opposite edge swap. And now the reason that we're going to do that is because I have to get this rotated back as well. So 2R, 2U, 2R, 2U, 2R, 2U. Okay. So this configuration here, as it is, ignore the center, these two need to be swapped, and these two are fine. This is a wild card. So to get out of this is another parity algorithm called the URF'd. So there's a Red Bull parity fixing algorithm and the URF'd parity fixing algorithm, which is very simple in this case. What you're going to do is, starting with here, 2U, 2R, 2F, then splitting it here, you do a 2U, and then up here, a 2U, then a 2F, 2R, 2U, and then at that point that flips that, and you're done with your solve. So you're tempted to do the same thing. Hold it over here and do URF this way. Here's the problem. On a supercube, when you do that URF algorithm, you do something else that you didn't notice on the side. You actually will rotate this center as well. So you're going to be in a very precarious position. This will swap, this will rotate to who knows where, but then you're going to have this center rotated, which means you're going to have two centers that are completely off. You could do that if you want, but there's maybe a better way to do that. What we have to do is, unfortunately, a pretty cumbersome sounding algorithm, which is a variation of the URF. Now, it's not a new algorithm. I've shown this before. I've done other supercube solves before. If you're going to be doing 4x4 supercube solves, sorry to say, this is something you're going to want to know, something you're going to want to keep to memory. The good news is it does flow pretty naturally and pretty fast. And what this does is this flip-flops these two without changing the orientation of this center or this center, or any of the centers. It'll be a pure flip-flop of these two. It's another URF variation, but just kind of bear with me to see what's happening with that. You're going to be alternating I moves and normal moves, so clockwise moves and counterclockwise moves. We'll start counterclockwise with a U, and it's going to be a middle U. So that's going to be UI, that's counterclockwise, R, that's clockwise, and FI, that's counterclockwise. So we still do the URF, and then we do the same type of thing, URF, but now we reverse it. Starting off with a clockwise, but it's a top U, we do a U, and then an RI, and a F. So that's not too hard to remember. You're just reversing it. Now you do a little bridge, you do a middle move, which is another middle U, and then a D. And now you reverse what you did before. So you're going to start off with an F, but it's going to be counterclockwise, so, and then alternate counterclockwise with clockwise. Fi, R, UI, and I'll do the same thing but start clockwise this time, so it's F, RI, and then stop there, then take just a middle D and move a middle D. So that's going to be D. And lo and behold, you will have swapped these two and nothing else will be different. Nothing else will be changed. If this were a 4x4, you'd be done by now. But this is a Megamorphix. And what we have here is we have another situation. We have a center rotation over here. And now how the heck did that happen?